Hello everyone, this is Greg from ChemCore. In this video, we're going to be going over the Bronsted-Lowry acids and bases explainer, or the actual worksheet. If you haven't had a chance to check out this worksheet, it is in the description below, as well as the answer key. And if you haven't watched the topic video of me explaining Bronsted-Lowry acids and bases, I really suggest you go check that out as well. Let's remind ourselves what Bronsted-Lowry acids and bases are. We can summarize by saying that acids are proton donors, while bases are proton acceptors. And actually, the first two questions is actually going to ask us about this exact thing. A Bronsted-Lowry acid is defined as a proton donor, so a proton donor, and a Bronsted-Lowry base is defined as a proton acceptor. And so these are two, nice questions to just remind ourselves what a Bronsted-Lowry acid and base are according to the definition. Now, in a lot of the questions in the rest of this worksheet, we're really going to work with using the Bronsted-Lowry definition to kind of explain the reactions that we can see. Okay, and now what I like to do is, especially when identifying the base and the conjugate acid, or acid and conjugate base, or acid and base, or any of the above, what I like to do is kind of define from left to right what is happening, right? If I can define everything, well then choosing out, for example, in this question, the base and the conjugate acid is going to be easy. And so what I can notice is that, well, this species kind of looks a lot like this species, except that it gained a proton. And so if it gained a proton, that means that this must be the base. All right? And conversely, number two, structure two, should be our acid. All right? Now, if the base became this and the acid became this, well, that means that structure 3 is our conjugate acid, and structure 4 is our conjugate base. Because if we were to read this kind of from right to left, well then now this guy donated to become this, and this guy donated to become this. Or this guy accepted to become this. And so in this question, we're asked about the base and the conjugate acid. Well, that means that we have structure 1, so we can kind of eliminate D and E. We have 1, and our conjugate acid should be structure 3. And so the answer choice should be B. The next problem, however, is actually asking us, with the same exact reaction, well, what is now the acid and the conjugate acid, right? And so we previously defined this as the base, this is the acid, and then if this was the base, structure 3 should be the conjugate acid, and structure 2, if this was the acid, then structure 4 should be the conjugate base. Which means that our Bronsted-Lowry acid should be structure 2, and our conjugate acid should be structure 3. And so our answer should be D. The next two problems are actually going to kind of have the same exact idea, where we have the same reaction, but they're going to ask for different things. And so what we can notice first is that H2SO4, this structure over here, looks a lot like this structure, except it lost one of the H's, or one of the protons, which means that H2SO4 should be the acid, which actually completely makes sense. If you remember from the previous acid and base video, we defined H2SO4 as sulfuric acid, which is a strong acid. In pretty much, I think, every example you're ever going to get, H2SO4, as well as the other strong acids, are going to be acids, they're not bases. Which means that if this was the acid, structure 2 should be the base. And then looking from right to left, the acid becomes the conjugate base, and the base becomes the conjugate acid. All right? And so if we're looking for the Bronsted-Lowry base, we have structure 2. And if we're looking for the conjugate base, we have structure 4. Which means that our answer choice should be E, or our answer should be E. Now in the next problem, again, this is kind of the same reaction. We define structure 1 as the acid, structure 2 as the base, and then structure 4 as the conjugate base, and structure 3 as the conjugate acid. Which means that our Bronsted-Lowry acid is structure 1, and our conjugate base should be structure 4, meaning that our answer is C. The last problem on this page is a different reaction in which we're still identifying Bronsted-Lowry. HCl is, again, one of your strong acids, and so you can kind of, rule of thumb, you can kind of assume that this is going to be your acid. But to ignore that kind of trick, we can notice that HCl becomes Cl-, which means we donated a proton. And so obviously this should be your acid. meaning that structure 2 should be the base. And now structure 4, HCl becomes structure 4, meaning that this is our conjugate base. And structure 3 is our conjugate acid. And so Bronsted-Lowry base is structure 2, and the conjugate base is structure 4. So our answer is E. In questions 8 and 9, we're kind of just being asked to use the definition of the Bronsted-Lowry acid and base to identify which one of these does not, match the definition. And so let's remember that a Bronsted-Lowry acid donates protons, meaning that we kind of have to have H in the structure, right? We have to have donatable H's. If we don't have H's in the structure, well, what protons are you going to donate, right? And so answer choice A obviously has a proton, and so we know that this definitely could act as a Bronsted-Lowry acid. Answer choice C has, again, a proton, and we know that it's a strong acid, and so we definitely know that it is a Bronsted-Lowry acid. Same thing with D. We have this proton and this proton, actually, and so we can eliminate D. And H2O, water, surprisingly, not surprisingly, we definitely do mention this in either this video or the next video. H2O can also act as an acid. It does have donatable protons. And so all of these have H's in the structure that they can donate, except for answer choice B or CBr4. In question 9, again, similar question, except now we're looking for which one doesn't match the definition for a Bronsted-Lowry base. And so remember that a Bronsted-Lowry base accepts protons. And so that means that we should have an atom that can become charged. Now remember, I've mentioned this, I think, in this video and kind of like many videos in the past. Every atom, or almost every atom, can become charged. We talked about this in the formal charges video. Oxygen can become positively charged, meaning it can gain another bond. Nitrogen can become positively charged, meaning it can gain another bond. I think even boron and phosphorus and sulfur and so many of the kind of larger atoms that we see in organic chemistry very often, except for carbon. Now, carbon is kind of our centerpiece of organic chemistry, and one of the important aspects is that carbon cannot accept an extra bond. It can't have 5 bonds. It could be positively charged, but only if carbon has 3 bonds and no lone pair. And so what we can notice is if we go through this example and we have atoms in the structure that can technically become protonated or get an extra proton and still be valid, well, then it is a Bronsted-Lowry base. And so if we look at structure A, we kind of have this little structure. Why can't we make it a positively charged oxygen? We definitely can. This definitely works. And so this definitely could act as a base. In this structure over here, why can't we make this another positively charged oxygen, right? This definitely works, right? I mean, is it happy? Does it want to be charged? No, but it's still possible, right? And so this definitely can act as a base. The next structure, why can't this become a positively charged nitrogen? We definitely could, right? That's the whole point of formal charges, right? And so this, again, could act as a base. And our last example, sulfur definitely, most definitely, can become positively charged. And so we know that answer choice E can also act as a base. Leaving D, right? There's no way that just carbons will become positively charged by accepting another bond, because it's not possible. Carbons can't have more than 4 bonds. And so we can choose D as our answer. In the next 2 problems, kind of like the problems earlier we discussed, we're identifying Bronsted-Lowry based on definitions or based on a reaction. And so if we look from left to right, I'm looking at this structure and then I'm looking at this structure. They kind of look very similar, except that, well, this one kind of has an extra proton and this one lost a proton, right? And so going from here to here, we kind of had to get rid of one of those extra protons, meaning that structure 1 is an acid, and then structure 3 must be the conjugate base. And structure 2, well, if structure 1 is the acid, we know that water must be the base. But just to make sense of it, if we go from number 2 to number 4, well, we somehow gain the proton. And according to the Bronsted-Lowry rules, we know that this must be the base, and structure 4 must be the conjugate acid. Meaning that our Bronsted-Lowry base should be structure 2, and the conjugate base should be structure 3. And so our answer must be D. In number 11, we're looking at the same exact reaction, and so realize that this one was our acid, structure 2 was our base, structure 3 was our conjugate base, and structure 4 was our conjugate acid. And so if we're identifying the base, again, we have answer structure 2, and the conjugate acid should be structure 4, meaning that our answer is E. In this question, remember that we just identified this, but just to recap, we identified that structure 1 donated a proton, and so this must be the acid. H2O accepted a proton, so it must be the base, meaning that looking from right to left, structure 3 must now be our conjugate base, and structure 4 must be the conjugate acid. And so the Bronsted-Lowry base is structure 2, and the conjugate base is structure 3. And so our answer is D. The next couple problems, we're still looking at the next reaction. So if you haven't looked at us, if you're skipping toward this question and you are, if you missed us breaking down the question, make sure to kind of skip back a couple to question 11. Again, we identified that this one donated a proton, so it must be the acid. H2O accepted a proton, so we know this must be a base. Structure 3 must be the conjugate base. Structure 4 must be the conjugate acid, meaning that our Bronsted-Lowry acid is structure 1, and the conjugate base must be structure 3. So our answer is B. Number 14, again, we identified structure 1 as donating a proton, and so it's the acid. Structure 2 accepted the proton, so we know it's the base. And structure 3 must be the conjugate base. And structure 4 must be the conjugate acid. And so our Bronsted-Lowry acid is structure 1, and the conjugate acid must be structure 4. So our answer is C. In the next problem, we're again kind of using the Bronsted-Lowry definition to identify the acid, the base, the conjugate acid, and the conjugate base. And so what I like to realize is that structure 1 kind of becomes structure 3, in which we lose that proton. And so if we lose that proton, this structure 1 must be the acid, and structure 3 must be the conjugate base. Now, if structure 1 was the acid, obviously structure 2 must be the base, but just to make sense, OH gains a proton to become H2O, and so this must be our base, while H2O must be the conjugate acid. And so the acid is 1, the base is 2, the conjugate acid is 4, and the conjugate base is 3, meaning that our answer choice is B. It's actually out of order, so just make sure that you're lining it up correctly. Number 16, which of the following is not a Bronsted-Lowry acid? This is very similar to one of the problems we had in the past. Remember that an acid, according to the Bronsted-Lowry definition, is something that donates protons. And so a lot of species in organic chemistry could technically act as Bronsted-Lowry acids as long as they have donatable protons. If they don't have donatable protons, they're not going to be Bronsted-Lowry acids. And so what we can realize is that H2O definitely can donate protons, and so it can act as an acid. NH4 is just going to become NH3, right? Ammonia. Definitely could donate that proton. This structure can definitely donate this proton to become something like this. Oops. And so we can definitely identify that this could be a Bronsted-Lowry acid. And now, this is kind of a typo. There should be a triple bond between here. And so this is something that we're going to discuss in a future video, in the video called Oreo. So if you haven't watched that video yet, go check that out. Alkynes, or triple bonded carbons, can definitely donate these protons, right? And so if you haven't watched that video yet, I really suggest it'll make more sense after watching that video. The only structure that can't donate protons are definitely kind of sp3 hybridized carbons, right? And all of these carbons are sp3 hybridized. There are no protons on the nitrogen. And so B cannot act as a Bronsted-Lowry acid. In number 17, we're again identifying according to Bronsted-Lowry definition, except now they're asking us for bases. And you might be confused, hold on, but we only have one base? Yes, but in equilibrium, it's happening backwards at the same rate. And so from the forward, we can have bases. Reverse, we kind of call them conjugate bases, but they're still bases, right? Because at equilibrium, it's happening forward and backward at the same rate. And so all we have to do is really identify which one is our base on the left and which one is our conjugate base on the right. And those should be our answers. And so if you notice, PO4 on the left kind of accepts a proton to become HPO4. And so this must definitely be our base in the forward reaction. While in the reverse reaction, OH accepts a proton to become H2O. And so this must be our base in the reverse reaction, mostly called the conjugate base, or usually called the conjugate base. In this example, I guess not. And so our answer should be B, PO4 3 minus and OH minus. The reaction between which combination of substances below cannot be classified as a Bronsted-Lowry acid-base reaction? Well, we're just trying to see which one of these substances, or which pair of substances, if they were to react, can either donate or accept protons. Both of them must kind of take one of those jobs. And so in A, well, this guy can donate the proton, and we can have CH4. Remember, this is a spectator ion. And this becomes C2H5O lithium, right? This definitely could act as a Bronsted-Lowry acid base, right? I just created an acid-base reaction. Okay, H2SO4, again, you should know your strong acids by now. This can definitely donate a proton and become HSO4. There should be an Na somewhere here, kind of, usually we write it in front. And then this would become CH3CO2H. Definitely could act. And now H3O plus can definitely donate a proton. Why H3O plus? You can watch the on Oreo. If you haven't watched that yet, it'll make a lot more sense. But this should become H2O, kind of makes it happier. And CH3NH2. And so if you're kind of thinking about this logically, well, we're trying to kind of take away the charges. And so if we were to donate a proton from H3O and give it to CH3NH, we would kind of get rid of all the charges and be happy. Now, NH3, kind of, I'm not exactly sure if it can donate the proton. It'll become NH2 with 2 lone pairs. So that's really not kind of stable for nitrogen. It really doesn't want to do that. But what I can tell you is that BF3 definitely doesn't want to accept a proton. BF3 definitely can't donate one because it doesn't have a proton to donate. So we have to, if this were to happen, BF3 has to be the base. But it's not going to happen, right? NH3 doesn't want to donate this proton, and BF3 doesn't want to accept it. And so we can say that C cannot be classified as Bronsted-Lowry. Maybe it does happen in a different definition, which we'll discuss in a future video. And the last 2 questions, again, are kind of summarizing this whole sheet that we've been doing with definitions. Again, you cannot repeat these definitions enough. They get really confusing, and so I really like to stress remembering definitions. According to Bronsted-Lowry theory, an acid is a substance that can donate a proton. And according to Bronsted-Lowry theory, a base is a substance that can accept a proton. These 2 questions conclude our worksheet on the Bronsted-Lowry acids and bases. Again, if you want to retry this worksheet, check out the description below for absolutely free copies and answer keys. And if you want to go over the video discussing Bronsted-Lowry acids and bases, go check out that topic video again in the description below. And I'll see you guys in the next video.